Okay, welcome everyone to this week's seminar. We're very happy to have Clara Bradley talking to us today. Clara did her undergraduate degree in physics and philosophy at Bristol before completing a degree in philosophy of physics at UC Irvine, and she's now an assistant professor at UCL. So we're thrilled to have her back in the UK. And super excited to hear what she has to say about a topic that we all love, namely sophistication and reduction. So over to you.
Cool, thank you, James. So, as James said, my talk today is on this question: are sophistication and reduction always viable alternatives? And this is joint work with Jim Weatherall, who was my supervisor, and it's very much work in progress, so I'd appreciate any suggestions you have about the talk. Okay. So the background to this talk are really two questions. The first one is, how do we identify when a theory has excess structure? So there's how do we identify when a theory has some parts of the mathematical framework of that theory that don't seem to have any kind of physical correlate? And then related to that, the question is, given that we can identify that a theory has excess structure, what should one do in light of the presence of excess structure? That is, how could one formulate a theory that doesn't have that excess structure? And there's this recent paper by Neil Dua, who basically suggests that there are sort of two alternatives as ways of removing excess structure. The first he calls reduction, and the second he calls sophistication. And these terms have kind of been absorbed into the literature more broadly as ways of discussing the different ways that we want to remove excess structure from a theory. But today what I'm going to do is I'm going to try and suggest that we should be at least a bit cautious about applying these terms. And in particular, what I'm going to argue is that the way that Neil defines these terms in his paper, and then the way that they get applied to cases in physics more generally, somewhat come apart from each other, and that really there are two different kinds of notions of reduction that can get conflated and that we ought to keep apart. Okay. So just to start with, I just wanted to go through a few cases of theories that people often talk about as having a kind of excess structure. So hopefully for those of you who don't know this literature so well, it'll help to sort of pump the intuitions about what excess structure is. And for those of you who do know this literature, I'll come back to all of these examples, so they're just there to keep in mind. So the first example, sort of the classic example of a theory with excess or surplus structure, is the case of Newtonian gravitation set in Newtonian space-time. So Newtonian space-time is just a space-time structure that foliates space-time into simultaneity slices, and in particular is such that it has a fixed standard of rest. And so the idea is that the sense in which this theory has excess structure is that the laws of Newtonian gravitation do not seem to depend upon what the standard of rest is. If we transform the standard of rest so that it's to some other inertial observer, then the laws do not seem to depend upon which one we picked. And so the sense in which we have excess structure is that it doesn't seem like the laws of the theory depend upon what the standard of rest is. So that's the first example. The second, more controversial example is the case of general relativity as exhibited by the Hall argument. So for those who don't know the Hall argument, the idea is that we start with some model of general relativity. So we just have a manifold with a Lorentzian metric on it. And then we think about acting on the points of this manifold by a diffeomorphism, and then pushing forward the metric along the diffeomorphism to generate some new model. And under some of these diffeomorphisms, what one finds is that there are some points of the manifold that are such that the metric at that point, there's a disagreement between the value of the metric across these spacetimes, and yet these models are isometric, and in as much as isometric models of general relativity have all the same kind of observable features, that is, the measurements that an observer will make is the same in these two models, it seems like general relativity has a kind of excess structure in the sense that there are these two models that disagree about the value of the metric at certain points, and yet there's some sense in which we think they ought to be equivalent. Okay. And then the final case is not a space-time theory, but rather a theory of electromagnetism, in particular written in terms of vector potentials. So the idea is that we take models of the theory to be given by some vector potential A on Minkowski spacetime, and the dynamical equations are just given by this equation of motion relating this vector potential and the charge current density, so essentially tells one how charges move within this vector potential. And what one finds is that if some particular vector potential A satisfies this equation, then so does the transformed A that corresponds to taking A plus the derivative of some scalar field X. And so again, the idea is that this theory seems to have a kind of surplus structure in the sense that models that have these different values of A, different A's related by these transformations, both give rise to the same equations, so there doesn't seem to be any kind of dynamical difference between them, and yet the theory distinguishes them. Okay, so what's supposed to be common to all of these cases is that there seems to be a kind of symmetry that relates models of a theory that, at least on a kind of naive interpretation, are inequivalent to one another. And it's this presence of the symmetry that seems to indicate that a theory has a kind of excess or surplus structure. And this leads to the following kind of doctrine. The doctrine is that we should do without surplus structure in our theories by equivocating between symmetry-related models. Okay, so now if we adopt this kind of doctrine, there are some natural questions that arise. The first is, are there really different ways that we can equivocate between symmetry-related models? That is, are there different ways that we can remove surplus structure from our theory by doing this kind of equivocating between these models that are symmetry-related? And the second question is, are the same kind of options available for all theories that we have that have what we think of as surplus structure? That is, are there always the same kind of ways to equivocate between symmetry-related models in all different contexts? Okay. And one kind of answer you might give comes from this paper by Neil, where he says that essentially reduction and sophistication provide distinct but equivalent ways of removing surplus structure in a variety of cases. So what's the difference between reduction and sophistication? Well, the idea is as follows. So firstly, what reduction involves is that what we do is we reformulate the theory in terms of quantities that are invariant under the symmetry, so that the new theory essentially does not have that symmetry, at least as a kind of non-trivial transformation. So the symmetry essentially just becomes the identity model on the identity map on our reduced model. So in this picture, the idea is we have two distinct models in our theory that we find are symmetry related. And so what we want to do is find what's invariant under that symmetry, so that these two models just correspond to one single model of our reduced theory, such that now the symmetry essentially just gets mapped to the identity map on this reduced model. Whereas sophistication is supposed to be this alternative, where instead of reducing the theory, what we do is we change the interpretation or the semantics of the theory so that the models are effectively rendered isomorphic within the theory. So the idea is that inasmuch as isomorphism is the standard of mathematical equivalence, if we can make it such that these models are isomorphic within the theory, then even though they're distinct models, we can provide a kind of interpretation under which they represent the same physical situation, and so we no longer have to think that they have any kind of excess structure. And Neil gives us sort of two ways of doing this. Either we can simply sort of stipulate that these models are isomorphic, which he calls the external method. And one way to think about this, if we think about theories in sort of category theoretic terms, the idea of external sophistication would be to simply sort of add arrows between the objects of the theory. Or the second option is that we use some kind of new mathematical tools to define the models of the theory, so that now with these new mathematical tools, the natural standard of isomorphism just coincides with the symmetries of the theory. And this he calls the internal method. So we have these two models that were symmetry related and distinct. We now keep that they're distinct, but we have that they're isomorphic to one another. So in order to motivate this distinction, Neil gives us a nice simple example of a first-order theory, which we're going to call the handedness theory. And this theory is such that it has two one-place predicates, L and R, and two axioms that essentially say everything either has the property R or the property L, and nothing has both. And so we can think of this theory as telling us that there are two kinds of objects in the world. There are left-handed objects and there are right-handed objects. So we can think of this visually as we're just going to take the models to be represented by essentially having these arrows that either point in the right direction or in the left direction. Okay. So we have this theory, and now what Neil says is that there's a symmetry in this theory. The relevant symmetry is the map that takes the predicate L to the predicate R and vice versa. So left to right and right to left. And why is this sort of a relevant symmetry to indicate that this theory has excess structure? The idea is that this theory doesn't seem to depend upon whether one's flipped the hands of every object or not, in the sense that if we say, for example, take the model that satisfies the sentence, everything is left-handed, if we imagine that we're sort of in that model with one of the hands in there, and then we imagine flipping all the hands in that model, including our own, there's a sense in which we wouldn't be able to distinguish whether we're in the model that satisfies the sentence, everything is right-handed, from the one where everything is left-handed. And so we might think that this symmetry indicates there's a kind of excess structure in this theory. So now we think about what are these two alternatives that we can do. So the first one, this reduced kind of option, the idea is that what seems to be preserved under these maps that flip the handedness is just what hands have the same handedness or not. And so what we can do is define the theory in terms of a congruence relation that tells us whether for two hands they have the same handedness or not. So then the reduced theory is given by axioms that just say that this relation C is an equivalence relation with, at most, two equivalence classes. So that's our reduced theory. And then what's our sophisticated options? Well, on the external method, the idea is that what we're going to do is we're going to sort of simply stipulate that these models related by flipping the handedness of every object are isomorphic. And the way we're going to do that is we're just going to define a homomorphism that's invertible from between two models that essentially is such that it can take the predicate L to the predicate R across these models and R to L, so that it doesn't need to preserve the extension of these terms L and R. And so essentially, these models that previously were not equivalent to each other, where we flip the handedness of everything, now are just made to be equivalent. And then the internal sophisticated option, the idea is that what we're going to do, remember, is sort of define the models now in terms of new mathematical tools so that the natural standard of isomorphism corresponds to the symmetry. So the way Neil says we can do this is that we can redefine the handed models in terms of essentially a two-element set that can be different for each model that takes the place of the predicates L and R. And for each model, we have a function that assigns to each element a subset of the domain. So essentially just gives the extension of these two predicates in this set. And so what this means now is that when we're talking about the sentences that we had in our original theory, such like the sentence, everything is left-handed, because there's now no way to determine which element of this two-element set for each model the predicate L refers to, there's no way to determine the truth value of that sentence without sort of in this ambiguous way, there's this ambiguity in terms of which of the predicates we assign it to, and so correspondingly what the extension of L is. And so these models that previously we could distinguish in terms of the fact that one satisfies the sentence everything's left-handed and the other one satisfies the sentence everything's right-handed, we now can't distinguish them in this way because there's no privileged way to assign L and R to these elements of this set. Okay. And now importantly, what Neil shows is that reduction and sophistication, both in the internal and external way, for this handedness theory are equivalent in the sense of categorical equivalence. And the reason this is so is that one of the sort of criteria for categorical equivalence is that there's essentially a bijection on the isomorphisms between the categories. And the reason this is so in this case of the handedness theory is just that every homomorphism of the sophisticated theory is a map that preserves the congruence of hands. and vice versa. Every map that preserves the congruence of hands is a homomorphism in sophisticated theory. So this is the sense in which sophistication and reduction provide distinct but equivalent ways to remove excess structure. Okay. But now, of course, we know that physical theories are not generally first-order theories, and so we need a way of translating the ideas about the handedness theory to the case of local field theories more generally. And Neal does provide a definition for symmetries for local field theories that's supposed to be analogous to the definition that he gives in this first-order case for the handedness theory. He says we can just think of them as being maps on the field variables that take solutions to solutions. And so the idea is if we take our example of electromagnetism with vector potentials, then the map that takes the vector potential A to A plus the gradient of the scalar field X is just a symmetry in precisely this sense. And then the story is supposed to go that the reduced theory is the one where we define the theory in terms of electromagnetic fields, since all of these A's that are related by the gradient of these scalar fields just correspond to the same electromagnetic field. And so it's supposed to be analogous to the congruence theory in that sense. And then the externally sophisticated theory is just the one where models whose vector potentials are related by the symmetry are simply stipulated to be equivalent. And the internally sophisticated theory, remember what we want is a theory whose where these symmetries now correspond to isomorphisms in the theory. And he says that the candidate theory for the case of electromagnetism is Yang-Mills theory. The reason is that models of Yang-Mills theory are given by connections on a principal U1 bundle over R, where the isomorphisms of such a theory are just the vertical bundle automorphisms that preserve the connection. And it turns out that these can be thought of as just representing maps of the above kind where we take A and we add the scalar field, the derivative of the scalar field. Okay. So that's the case of electromagnetism. But this idea of sophistication as a way of removing excess structure is also supposed to apply to space-time theories. And space-time theories are such that their symmetries are not necessarily maps on the field variables, but rather are maps that permute the points of the manifold and then push forward the fields along the permutation, just like we had for the case of general relativity. And indeed, the term sophistication, as Neal coins it, essentially might be thought to come from an interpretive stance in general relativity called sophisticated substantivalism, which most of us here know is just the view that space-time is a physically real entity, but distinct but isometric models of general relativity don't correspond to distinct possibilities. So how is this sort of sophisticated substantivalist view and sophistication in Neal's sense supposed to be related? Well, if we take our models of general relativity related by this map, this whole argument map, if we take these kind of models, then there is a kind of disanalogy with how we had in the handedness theory case, because these models are essentially already isomorphic in general relativity, and so we don't have sort of two non-isomorphic models that we want to remove excess structure from. But what we might say is that general relativity just is the internally sophisticated version of some other theory where these models are not isomorphic. So, for example, one suggestion is that really what the whole argument shows is that there is excess structure for a theory that's given by general relativity plus something, where that something, for example, could be having like a fixed label attached to points of the manifold. And then general relativity, as given by models of Lorentzian manifolds, would just be the internally sophisticated version. And then we might think that sophisticated substantivalism is then sort of the natural interpretation of the sophisticated formulation. It's just the way that we can interpret models that are sort of distinct but isomorphic in such a way that they correspond to the same physical situation. And the idea of sophistication in Neal's sense might be thought of as saying that we can apply that kind of methodology to all sorts of theories. And similarly, we might think that we can say something like the following. If we take the case of Newtonian gravitation set in Newtonian space-time, when we remove the standard of rest in Newtonian space-time, we might say that we get the internally sophisticated theory the theory given on Galilean spacetime, whose isomorphisms are just the diffeomorphisms that preserve the classical metrics and the derivative operator. And the sense in which this is sophisticated as these isomorphisms can just be thought of as the ones that relate the difference or standards of rest that we had in the original theory on Newtonian spacetime. We can just think of them as including the Galilean transformations. Okay. So it's at this point that I want to pause and ask ourselves, is the way that we thought about sophistication here in the case of spacetime theories really the same as what we thought about them or how we thought about them when we were talking about the handedness theory case in the case of these first order theories? And in particular, I'm going to raise a kind of problem for this distinction between sophistication and reduction in the case of spacetime theories and more generally for the case of local field theories. The problem essentially that I'm going to raise is the following. The kind of symmetry that's exhibited by these supposedly internally sophisticated spacetime theories is in essence present at all local field theories. And so, if reduced theories are supposed to be those theories without symmetries, which is at least one way to think about how they're being defined in the first order case, then what we find is that no local field theory comes out as reduced. But if we take the other option and we don't allow such maps to count as symmetries, then what we're going to find is that several local field theories, not only general relativity, but also Yang-Mills theory, come out not as sophisticated, but rather as reduced. And so this distinction between sophistication and reduction seems to somewhat collapse in the case of these local field theories. At least that's what I'm going to suggest. Okay. So the rest of the talk's going to go as follows. I'm first going to say why I think this problem actually already arises in the case of first order theories, but I'm going to suggest that there's a kind of response that one can give in the case of first order theories that maybe allows us to keep the distinction clear in that case. And then I'm going to turn to why I think this problem is really a problem in the case of local field theories, and in particular why the response that one can give in the first order case doesn't really help us in the case of the local field theories. Then what I'm going to do is I'm going to talk about whether there's a way to recover the distinction between sophistication and reduction in light of what I've said earlier, and in particular, how we might capture the intuition that people have had that there is this clear distinction between the two. And it's there that I'm going to argue that really there's sort of two notions of reduction that are getting conflated. And then I'm going to end just with some more broad lessons from this. Okay. So talking about the first order case, let's first think about more carefully how Neal defines symmetries in the first order case. So the way that he defines symmetries is as a translation from a theory to itself, which we might call an auto-translational equivalence. So what is this? The idea is that there are what we call dictionary maps, maps that take predicates of the theory to formulas of the theory, such that for any formula, T proves that formula only if it proves the translated version of it. And for any formula, T proves that phi is this formula is equivalent to the composition of two of these dictionary maps acting on phi. So we can think of this as there being essentially an inverse dictionary map that takes this formula back to itself, and likewise with these, the composition of these maps reversed. And so, for example, in this handedness theory, the idea is that the dictionary map is just the one that takes the formula Lx to Rx, and it takes Rx to Lx, and it's its own inverse. Okay, so there are a couple of observations that I want to make here. The first observation is that this definition is such that it doesn't count permutation maps as symmetries for first order theories, even though these maps can be isomorphisms of the models of the theory. The reason it doesn't count permutation maps is just that these dictionary maps are such that they take predicates or formulas of the theory to other ones. They don't act by acting on the domain of the models. And there's a sense in which one can't count them as symmetries if one wants to say that the congruence theory is a theory that doesn't have any symmetries, since the congruence theory does have symmetries in precisely this sense. Namely, we can permute the domain of a model of the congruence theory such that it preserves how many objects are in each congruence class, and this is going to be a symmetry in precisely this sense. And more generally, we might say any first-order theory is such that one can permute the domain and appropriately change the extension of the predicates or relations so that the resulting models are isomorphic. Indeed, this is kind of the insight of Putnam's permutation argument. So this is the first observation. The second observation, though, is that even if we don't think about permutation maps as the relevant kind of symmetries, even in Neal's definition of symmetries, there is a symmetry that the congruence theory has. Namely, it has an auto-translational equivalence given by the dictionary map that takes the proposition or the predicate cxy to cyx. And so if we think that this is a symmetry in Neal's sense, and if reduced theories are supposed to be theories without any symmetries, then we have two options. Either we can think really the congruence theory is only partially reduced, or we can think that the congruence theory is reduced, but we just don't think that that map counts for the purposes of saying whether a theory is reduced or not. So let's think about these two options in turn. For the first one, what this would mean is that there's some other theory that we can define that can essentially remove this symmetry corresponding to this map that takes cxy to cyx. But I don't see that there's any way that this could be viable while also preserving the content of this congruence theory, since this symmetry, this map, is precisely just what essentially corresponds to one of the axioms of the theory, namely that the congruence relation is symmetric. And it's not clear how we would capture the content of this congruence theory, namely that we have this equivalence relation, if we try to get rid of this kind of symmetry. And so this leaves us with the second option, that we should think that the congruence theory is reduced, but we don't think that that map, that dictionary map, is one that counts for the purposes of saying whether it's reduced or not. So if we take this option and say that not all symmetries count for the purposes of evaluating whether a theory is reduced or not, then the natural question is, well, what determines whether a symmetry counts? And indeed, if we think about that congruence case, it seems that we don't want to count this symmetry precisely because it's not the sort of symmetry that we would want to reduce, given the content that we want the theory to capture, namely facts about the congruence between hands. And indeed, it seems like the congruence theory says just what we want it to without any kind of redundancy. So I think what this suggests is that whether a theory is reduced depends not on formal considerations, just on formal considerations about what a symmetry is, but also on some background assumptions about what it is that we actually want to be able to capture in our theory. What is the content that we actually want the theory to capture, and what kind of symmetries do we need in order to capture precisely that content? Okay, so with that in mind, let's now turn to the case of local field theories and see how this problem arises in this context. And indeed, the first thing to consider is the definition of symmetry that Neal gives us for local field theories, namely as maps on field variables that preserve solutions. And if we just think about symmetries in this sense, then I think we have exactly an analogous issue to the case that we had with the congruence theory. So for example, if we think about the reduced electromagnetism theory given by the Faraday tensor formulation, then there's a sense in which it has a symmetry in precisely this sense. We can just think about the map that takes FAB to minus FBA. Just like with the congruence theory, this is not a symmetry that we think we want to reduce, precisely because it seems that it's required in order to express the fact that our Faraday tensor is anti-symmetric. And so likewise, it seems like there are these symmetries that this theory has, but not ones that we think say that this theory is only partially reduced, precisely because it's the kind of symmetry that we think we need in order to capture what we want this theory to say. But there's also a difference with the first order case. The difference is that, unlike in the case of first order theories, we can't consider these permutation symmetries to not be of the relevant kind if we want to say that, for example, that general relativity is a sophisticated theory. And more generally, it seems like we need to allow, in the case of local field theories, that diffeomorphisms that preserve the structures defined on the manifold, or in other words, that relate isomorphic models of such theories to count as symmetries, precisely if we want to capture this intuition about what are the sort of sophisticated theories in this context. But this now takes us back to what I take the real problem to be here, which is that it's not just space-time theories that have these kind of symmetries. There's a sense in which all local field theories have symmetries in precisely this kind, in the sense that we can commute the domain of commute the points of the manifold and push forward the structures along that, such that the resulting ones are isomorphic. And so there are no reduced theories in the sense of having no symmetries in this sense. And so we might try and make the same kind of move that we made in the first order case, or the case of the symmetries in this other sense, and just say that some of these symmetries count for the purposes of saying whether the theory is sophisticated or reduced. Something like reduced theories should be thought of as only having the symmetries that are needed to express the content of the theory. But this takes us to what I think is the crucial point here, which is that if we think about, for example, the case of general relativity, the isomorphism that we have between the models in the whole argument, or more generally, the map between models where we have this push forward along the diffeomorphism of the metric, such that they're isomorphic, is precisely what one would expect if one has captured the fact that models of general relativity have the structure of a Lorentzian manifold. Indeed, it's not clear in the same way as we had for the case of the symmetries of the congruence theory or the Faraday tensor formulation, what it would mean to reduce this theory while keeping the content of the theory the same. So in this way, I think if we take this analogy with the first order theory seriously, it really thinks that what we really should say is that we should think of general relativity as a reduced theory. It's a theory like the congruence theory that symmetries are precisely the ones that we think we need in order to capture the content of that theory. And so the sense in which reduction and sophistication in Neil's sense and sophisticated substantivalism comes about as an interpretation for general relativity, I think somewhat come apart. We might think that general relativity is really a reduced theory, and so sophisticated substantivalism perhaps is just an interpretation towards a reduced theory in this sense. But this problem goes even further, which is that I think equally on this kind of picture, Yang-Mills theory also looks more like a reduced theory than it does a sophisticated theory, in the sense that its symmetries seem to precisely be a feature of the theory required to express the fact that models of electromagnetism have the structure of a connection on a principal U1 bundle. So in this way, it's just like general relativity in that its symmetries are precisely the ones we need to capture the content of the theory. And so inasmuch as both Yang-Mills theory and the Faraday tensor formulation are these well-defined theories of electromagnetism without the excess structure of the vector potential formulation, I think there's a sense in which they both should be thought of as reduced theories by analogy with the first order case. Okay. So just to summarize, what I've suggested is that local field theories, just like the first order theories, are such that there are symmetries whose existence doesn't seem to license us saying that there's some further reduced theory that captures the same content. And the symmetries of space-time theories, and by extension, symmetries relating isomorphic models of any kind of local field theory, seem to fall into exactly this class. And so we ought to think of theories with just these kind of symmetries as reduced theories. Okay, so this now takes us to the next part of the talk, thinking about, in light of what I've just said, is there a way to recover the distinction between sophistication and reduction? And in particular, what we might want to say is, no, there is a clear distinction between Yang-Mills theory and the Faraday tensor formulation. The difference comes down to the fact that Yang-Mills theory has a way of representing the symmetries of these vector potentials that the Faraday tensor formulation just doesn't have. So we might say something like, okay, rather than defining sophistication and reduction in terms of whether a theory has symmetries of a certain kind, we might instead think about the distinction in terms of how a reduced theory is actually constructed. So we might say, for example, the Faraday tensor formulation is reduced not because it doesn't have any symmetries, but because it removes the symmetry that we had in the vector potential formulation. It removes this kind of symmetry from it. Whereas Yang-Mills theory is sophisticated because there are these non-trivial isomorphisms of Yang-Mills theory that can be thought of as precisely representing this map. Okay. And more generally, we might say, physicists and philosophers often talk about the idea of reducing symmetry via a process of something like quotienting, often our phase space, that's the sort of big three-dimensional space represented here. And then what we find when we have gauge theories is that when we have in context of gauge theories, what we find is there might be certain constraints where these constraints define some submanifold of our phase space, such that this constraint surface is such that we can foliate it in terms of what are called gauge orbits, where the gauge orbits are just the integral curves of the null vector fields of the two-form that's induced on this constraint surface, where importantly it turns out that there's a well-defined way of essentially equivocating between the points along the gauge orbits, which we might think of as just these symmetry-related points. The way we can do this is we can define some reduced manifold where the points of this reduced manifold are such that each point corresponds to all of the points along the gauge orbit. And it turns out one can define a well-defined symplectic two-form on this reduced space, and so we can give rise to a well-defined dynamics on this kind of reduced space where we've essentially quotiented out the gauge symmetries. And so we might say something like the following: symplectic reduction is just a well-defined procedure and leads to a theory that effectively removes symmetries. So why can't we say something like reduction for local field theories is captured by the process of symplectic reduction? This is this well-defined thing that gets rid of symmetries. Is that precisely what we mean by reduction? And there are indeed some similarities with the way we thought about reduction in the first order case, in the case of the handedness theory, for example. For one, symplectic reduction is such that we can think of it as defining the theory in terms of the invariance under some symmetry transformation. Namely, we think about the symmetry transformation as being the transformations along these gauge orbits, and now the functions that we could define that differ along the gauge orbits are now not defined on the reduced space, so we might think there's a sense in which it just captures the invariant content. And we might think it kind of captures the case of electromagnetism in the sense that the Faraday tensor formulation is essentially equivalent to the symplectic reduction of the Hamiltonian electromagnetism theory, at least in certain topological cases. And finally, we could imagine thinking about formulating a space-time theory in this kind of phase space way, such that we can reduce its symmetries via symplectic reduction. So maybe what we mean by reduction for these space-time theories is just something exactly of this kind. Okay. But what I want to suggest is that there are also some important dissimilarities between what's going on here and what's going on in the first order case that we discussed before. The first kind of dissimilarity is that the theory that one symplectically reduces, there's a sense in which that theory is not a theory with excess structure. So if we take the example of the sort of Dirac procedure we had in that picture, if we think about the models of the theory as being given by models on this constraint surface with this induced two-form, where the isomorphisms are just given by the diffeomorphisms that preserve this two-form and the Hamiltonian, then I claim it's true that gauge transformations, these sort of symmetries, are automorphisms of this structure. And so there's a sense in which these gauge transformations are already isomorphisms within this theory. Okay. So if that's the case, one might say, well, can't we just say that the theory that gets symplectically reduced in this way is just an internally sophisticated theory? So just like we're saying that generativity is an internally sophisticated theory, can't we say that what symplectic reduction is a way of saying what the relationship is between an internally sophisticated theory and a reduced theory in this sense? Okay, this is what I take to be the crucial point, which is that we can say this, but if we do so, then we have to give up on the idea that sophistication and reduction are always going to be equivalent. So remember that we said in the first order case that one thing that hold of the sophisticated and reduced alternatives in the handedness theory was that they give rise to categorically equivalent categories. What I claim is true is that it's not the case that we have categorical equivalence between the models on this sort of constraint surface that get symplectically reduced and the symplectic reduced theory. To see this in this particular example I gave, it comes back to this proposition I just gave that the gauge transformations correspond to these non-trivial automorphisms of the structure of these constraint surface. And so when we have these non-trivial automorphisms that now correspond to a model of the reduced theory that just has a single automorphism, what one's going to find is that the map between the arrows of these two categories is not bijective. Really, in fact, it's not going to be injective. And so what one actually finds is that the functor between these categories forgets what's called stuff, essentially precisely that this functor is not injective. And so what are we supposed to take from this? Well, what I think one should say is something like the following. Really, there's two different kinds of redundancy that's at issue when one considers whether to undergo symplectic reduction and whether one's considering whether to undergo something like sophistication versus reduction. And in particular, in the kind of symplectic reduction case, the kind of redundancy we have is that there's a kind of interpretational ambiguity regarding the points along the gauge orbits, in the sense that we have these distinct points that seem to be able to represent the same physical situation. But it's not the kind of thing that indicates that we have excess structure. Rather, it's what me and Jim have previously called a kind of representational redundancy. We can use the automorphisms of a theory to represent a situation in lots of different ways. But although we can remove this kind of ambiguity, we shouldn't think that doing so keeps us with being able to capture exactly the same kind of content. In fact, doing so can change the content of the theory, and indeed in this paper we show that removing it can actually lead to adding structure to a theory. And what's sort of interesting here is that this relationship between these categories as we had for the symplectic reduction is precisely what one finds between Yang-Mills theory thought of categorically and the Faraday tensor formulation. They're not categorically equivalent, they're inequivalent in precisely this way where the map between the functor between the categories forgets stuff. It's not a categorical equivalence. And so what I think we should say is that they both capture the equivalence between symmetry-related models of the vector potential formulation. So they're both reduced theories, but they do so in non-equivalent ways. And so which one we should think is the right theory depends exactly on what one actually wants to be able to represent. So just to summarize, what I've said is that cases of local field theories where we seem to have this clear distinction between the sort of internally sophisticated and reduced options really seems to be the case where we can think of one theory as being the result of something like symplectic reduction where we quotient out symmetries. But when doing so, the resulting theories might not be structurally equivalent, nor might they be motivated by the same kinds of considerations. And so what I think we should say is that there are really different notions of reduction that capture different ways that we might reformulate a theory. Okay. So just to end with some sort of takeaway lessons that I think we should take from this. The first lesson is that while I think it's probably true that external sophistication is well defined in the sense that it's clear what it would be to simply stipulate that certain models are isomorphic within one's theory, internal sophistication is not always a clear alternative to reduction, in as much as both involve moving to a theory whose isomorphisms capture what we take to be the sort of right equivalences between models of the theory. The second kind of lesson is that there can be more than one reduced theory relative to some theory with excess structure. There can be more than one way that we remove that excess structure. And in such cases, we might think that we might be able to see that one theory essentially quotients out symmetries of the other. But in that case, there's just a question now of which one best matches our other needs, given that they might have different amounts of structure, or I said different amounts of stuff in this categorical sense. And the final, which I think to be maybe the most important lesson here, is that whether a symmetry indicates that we have any kind of redundancy, or whether it indicates the possibility of any kind of further reduction of the symmetry, depends on our background commitments about what it is that we actually intend the theory to be able to express. It's not just the kind of thing that we can look at sort of purely formal considerations in order to say. Okay, that's everything.